Hello everyone, I am Dr. Saida Aisha. Chemistry of transition elements is the unit which comes under the inorganic chemistry part of the syllabus. In this session, I would like to discuss the general characteristics of the transition elements, which include the catalytic activity, complex formation, and the interstitial compounds of the transition elements, taking in particular the 3D, 4D, and the 5D series elements. Let us see the first property in this session, which is the catalytic activity. As we know that the catalysts are the substance which influence the rate of the chemical reaction. That is, they are the substances which can alter the rate of the chemical reaction. Many transition elements and complexes are used as catalysts which influence the rate of the chemical reaction. The rate of the chemical reaction increases by the decrease in activation energy of the reactants. This decrease is caused by the catalyst which probably alter the path of the reaction. Transition metals and their compounds function as catalysts either because of their ability to exchange the oxidation state. In the case of metals, to absorb other substances onto their surface and activate them in the process. The bonds are formed between the reactant molecules and the atoms present on the surface of the catalyst, which results in the formation of reaction intermediates which provide a path of lower activation energy and therefore increases the rate of the reaction. If we consider a reaction where A and B are the reactants, and when they react in presence of a catalyst, it gives an intermediate of the form A, B and C. So this intermediate again gives the product A-B and the catalyst is regenerated. Or in other words, we can say that the catalyst is regenerated during the reaction. The transition metals show catalytic behavior mainly because of the following reason. They have the presence of the vacant d orbitals. Second, they have the ability to exhibit the variable valency or the variable oxidation state. And the last one is they have the tendency to form complex compounds. So these three factors contribute that the transition metals show catalytic behavior in many of the reactions. Some of the examples where transition metals are used as catalysts are iron, which is a transition metal belonging to the 3D series, is used in the Haber's process. Nickel is used in the hydrogenation of C-double-bond-C compounds. Vanadium oxide is used as a catalyst in the contact process. Likewise, iron ions are used in the reaction between persulfate ions and iodide ions. The next property in this session is the complex formation. Transition metal complexes or coordination complexes are molecules which contain groups arranged around a central metal ion. The transition metal form a large number of complexes. So in a way, these are like the LEGO molecules, which means that they are easily assembled from the smaller parts, and sometimes they are easily transformed into new molecules by switching out old parts from the new ones. We can also say that the transition metal complexes offer distinct advantages as the DNA binding agents. Here we can see an example for a complex compound, which is hexamine cobalt 3 chloride. In this, cobalt is the transition element present. Ammonia molecules are the ligands present in the complex compound. Hexamine cobalt 3 chloride is an example for a coordination complex. The transition metals have a tendency to form complexes, which is due to two factors. The metal ion present in the transition element is very small in size, and because of the small size, it has a high positive charge density, which makes it capable of accepting the lone pair of electrons from the molecules or ions, which are called as ligands. That is, the metal ions accept the lone pair of electrons from the ligands. They also have a vacant orbital, and these orbitals, that is the d orbitals, have the right type of energy to accept the lone pair of electrons from the ligands. Interstitial compounds is one more property of the transition elements. A number of interstitial compounds are formed by the transition metals. The d block elements form interstitial compounds with small non-metal atoms such as hydrogen, carbon, nitrogen, boron, silicon, and others, due to the ability of the metal lattice to accommodate the non-metal atoms between the metal atoms without the distortion of the structure. As the vacant spaces of the transition metals are filled up by small atoms, these compounds so formed are hard and rigid. The interstitial compounds of transition elements like hydrides, borides, carbides, and nitrides are prepared by heating the metal, that is the transition metal, with hydrogen, boron, carbon, nitrogen respectively. Hydrides are formed by heating with hydrogen, borides are formed by heating with boron, carbides by heating with carbon, and nitrides are formed by heating with nitrogen. The interstitial compounds have the properties of alloys. Therefore, they are extremely hard, possess good electrical conductivity, and they have a high melting point. The interstitial compounds are chemically inert except towards the strong oxidizing agents. One of the striking properties of the transition metals is the formation of non-stoichiometric compounds, which often exhibit semiconductivity, fluorescence, and they behave as heterogeneous catalysts. This non-stoichiometry is due to the defects in the solids. For example, if we consider an interstitial compound like iron 2 oxide, the actual analysis shows that the formula varies between Fe 0.840 to Fe 0.940. These are some of the references which have been used in preparing this session. I thank you all for hearing this session on the general characteristics of the transition elements. Thank you.